Okay, honors chemistry people, today we are going to learn how to balance chemical equations. The year is almost halfway gone and we're finally getting to actual equations. So here we go, Chapter 10, Chemical Reaction Types and Balancing Equations. Okay, chemists use statements called equations to represent chemical reactions. You've seen a couple of them already. Equations show a reaction's reactants. So when we look at reactants, they are the things on the left-hand side of the equation, or the things that we start with. And products, these are the things that are on the right-hand side of the equation. They are the things that we end up with, or the substances that are formed during the reaction. Okay? Chemical equations do not express numerical quantities as mathematical equations do, because during a chemical reaction, the reactants are used up and the products form. So we can't say one thing equals another thing. What we're saying is the reactants react to form this, okay? So instead, the equations used by chemists show the direction in which the reaction progresses. Therefore, an arrow rather than an equal sign, so we use an arrow rather than an equal sign, is used to separate the reactants from the products. You should read the arrow as react to produce or yield. It's not equal, but it reacts to make or yield or produce the following. Okay? The reactants are written at the left of the arrow. The products are written at the right of the arrow. When there are two or more reactants, or when there are two or more products, a plus sign is used to separate reactants and products from each other. Okay? Equations, symbols, are used to show the physical states of the reactants and the products. Reactants and products can exist as solids, liquids, or gases. Okay, so let's just do the symbols really quick. So solids are designated by an S in parentheses. Liquids are designated by a lowercase l in parentheses. And gases are designated by a lowercase g in parentheses. Now, when they are dissolved in water, we talked about this a little bit. Remember, dissolved in water is aqueous, okay? So dissolved in water is AQ. It means it's dissolved in water, okay? It's important to show the physical states of a reaction's reactants and products in an equation, because the physical states, whether solid, liquid, gases, or dissolved in water, give us clues to how that reaction occurred. Some basic symbols used in equations are found below. So let's look at this table down below. So we will use a plus sign to separate out reactants. We will use an arrow to designate reactants from products. Reactants will be on the left-hand side, products will be on the right-hand side. We will use what is called a reversible arrow. Indicates a reaction that can go both ways. So I will have it going forward and backwards. This is what we call an equilibrium reaction. Okay, and we will get into that a little bit later. S in parentheses is solid state, L is liquid state, G is gas, and AQ represents dissolved in water. Okay, so these are the symbols that we will use all the time in reactions. All right, so let's look at how we would construct a reaction. So here we go. Let's write this word equation using symbols below. So this is where our formula writing is going to come in handy. So if you're not sure on your nomenclature and your formula writing, this is where it comes useful. So aluminum, the symbol for aluminum is Al, and it's a solid. So I'm going to say it's a solid. Bromine. The symbol for Br is Br, but the thing about bromine, it's kind of tricky. It is what we call a diatomic molecule. And there are a whole bunch of diatomic molecules on the periodic table. Let's just take a minute to list them, okay? Now, I like to list them in a certain order, and you'll see why. Bromine is diatomic. Iodine is diatomic. Nitrogen is diatomic. Chlorine is diatomic. Hydrogen is diatomic. Oxygen is diatomic, and fluorine is diatomic. Now, all of these gases can bond with other things and bond with any number. So they could have a 1 or a 3 or a 4 or 5. But when they are by themselves, meaning that they are elemental, when they are by themselves, they bind to another atom in groups of 2. This is what I mean by diatomic. The reason I listed it this way is when you read these elements from left to right, it spells out the last name, Brinkelhoff. And that's a really easy way to remember the diatomic elements. So if you remember Brinkelhoff, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, these are all diatomic when they are elemental, when they are bound to just themselves. Okay? All right. So bromine is going to come in groups of 2, and it's going to be in the liquid state. And then I have aluminum bromide. This is where I need to look at my periodic table and look at the charges that we're going to acquire. So let me look at my ions periodic table. Let's open this one up. Okay, so if I look at aluminum, aluminum is a +3. Okay, and bromine here, bromine is in our -1 column. So aluminum is going to be a +3, and bromine is going to be a -1. So what ratio am I going to use to put this together? Hopefully you said 1 aluminum and 3 bromines to balance out that charge, to get that overall charge to be 0. And it is a solid, so I'm going to put solid here. Okay, so let's try this one. Solid carbon, so carbon's in the solid state, reacts with solid sulfur. To produce liquid carbon disulfide. Di means I've got 2 sulfides. So 1 carbon and 2 sulfurs. And it's going to be in the liquid state. Okay, so that's what we do to create reaction equations. Now, just to give you an idea, on the left-hand side, we have our reactants. On our right-hand side, we have our products. Okay, and this reaction arrow produces or reacts to form or reacts to make, any of those things we can use. It's not an equals, it's a reaction. This produces that. Okay? All right. So let's move on here. There are 7 elements that cannot exist by themselves, even when they are isolated from any other type of atoms. We already went over them. Elements of this nature will combine with atoms of the same element in order to be stable. I'm going to highlight them again. They are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So when we write them in order like this, it spells the last name Brinkelhoff. Okay? It helps you remember which elements are diatomic. Okay? So this is a list of the diatomic elements, meaning they come in groups of 2. Okay? You will notice that the equations that we did up top are not balanced. This means that there are not the same number and types of atoms on both sides of the equation. This breaks the law of conservation of mass, right? The law of conservation of mass said that I can neither create nor destroy matter. So that means I have to have the same number and type of atoms present on both sides of a chemical equation. Okay? We do not balance the state symbols. Those are basically ignored when we're balancing equations. But what we do pay attention to is the elements and how many of each are on each side. Okay? So, to balance equations, we must find the correct coefficients. So it's kind of like math. We're using coefficients for the chemical formulas in the skeleton equations. So a skeleton equation are the equations that we wrote. They don't have any coefficients. They just tell us what the products are and what the reactants are. That's what a skeleton equation is. A coefficient in a chemical equation is the number written in front of a reactant or a product. Coefficients are usually whole numbers. For now, we are going to use whole numbers, okay? And we don't usually write it if the value is 1. If the value is 1, just like in algebra, if you have 1x, you don't write 1x, you just write x, okay? So if you just have 1, the 1 is implied, okay? The coefficients in a balanced equation describe the lowest, and I can't emphasize this enough, it is the lowest whole number ratio of the amounts of all the reactants and products, okay? Subscripts, and I'm going to highlight this too. This is super important. I'm going to put it in bright pink. Subscripts. So subscripts in a formula are never, ever changed. Ever. You do not mess with the subscripts, okay? You only change the coefficients. That's all you can change, okay? So the best way to learn how to balance an equation is to practice. So we're going to spend some time practicing. Now, I like to go through element by element and just look and see what's on both sides of the equation and see what coefficient I need to play around with, okay? So we are going to just go element by element. So in this first example right here, we've got 1 copper on our reactant side, and we've got 1 copper on our product side. So we're good. Here we've got 2 oxygens on our reactant side, and I've only got 1 oxygen on my product side. So what can I multiply my product side so that I can get 2 on both sides? Did you say 2? So when I multiply it by 2, I have to multiply the whole molecule. I can't put in subscripts. I can only put in, you guessed it, coefficients. Okay, I can only put in coefficients. So doesn't that mean then that I have 2 coppers right here? It does. So that means I have to go back and I need to multiply my coppers on my reactant side by 2. Okay, so let's look at our next one. Potassium. I've got 1 potassium and 1 potassium, so it looks okay. Okay, I've got 2 hydrogens, and I've got 1 here, and I've got 2 here. I've got 3. That could be a problem. I've got 1 oxygen here, and I've got 1 oxygen here. Let's see. So, let's try multiplying our potassiums by 2 and our hydrogens by 2. Let's just see what that does. Okay, so if I do my potassiums by 2, that means I need to multiply my potassiums on my product side by 2 as well. So that gives me 2 potassiums. Okay, Now, if I look at my hydrogens on this side now, 2 times 2 gives me 4 hydrogens. 2 times 2 gives me, or 2 times 1 gives me 2 right here, and then 2 right here gives me 2 more. So 2 plus 2 is 4. So my hydrogens do work. Now let's double check and make sure my oxygens work. So 2 times 1 gives me 2 oxygens, and 2 times 1 gives me 2 oxygens. So that works. So I need 2 potassiums, 2 waters, 2 potassium hydroxides, and 1 hydrogen. Okay? How'd you do on that one? All right. Now, let's look at this next one. Element by element. Okay, calcium. We've got 1 calcium and 1 calcium. We're okay. We've got 2 chlorines and we've got 2 chlorines. No, we don't have 2 chlorines. We've got 1 over here. So I'm going to go back and I'm going to put a 2 here. Okay, so I've got 2 sodiums, and with that 2, I now have 2 sodiums. So I'm good here. And then look at this. SO4 and the group is the same. So if the group stays the same on both sides of the equation, balance it as the group. So if I have a polyatomic like I do here, I can't spell, polyatomic, and it stays as a group on both sides of the equation, balance it as a group. It makes it so much easier if it stays the same on both sides of the equation as a group and it doesn't break apart, to balance it as a group. Okay? So I've got 1 sulfate and I've got 1 sulfate. So it looks like I'm balanced here. Okay? Let's look at this next one. Ooh, we do have a polyatomic on this next one. I've got ammonium. But do I have ammonium on the other side? No, I don't. It breaks apart. It does not stay together. So when it doesn't stay together like this, you're going to have to piece by piece or by element balance it. Okay? It makes it a little bit harder, but you can do it. I have faith in you. Okay, we're going to take element by element. So this 2 right here multiplies this whole group. So that means I've got 2 nitrogens, and on this side, I've got 2 nitrogens. So I'm doing pretty okay. And here, 2 times 4 gives me 8 hydrogens. And here I've got 2 hydrogens. So what can I multiply 2 by to give me 8? Did you say 4? 4 times 2 does give me 8. So my hydrogens are now okay. I've got 2 chromiums. And here I've got 2 chromiums. So I'm okay there. And then I've got 7 oxygens. I've got 3 right here, plus 4 times 1 is 4. So 3 plus 4 is 7. So my oxygens work out. Okay? All right, let's do this next one. Now this next one, when we have carbon, hydrogen, and oxygen in an equation, and the whole equation is only carbon, hydrogen, and oxygen, I want you to do a special thing here. So if I have just carbon, hydrogen, and oxygen in an equation, I want you to do carbon first. Balance carbon first, balance hydrogen second, and save oxygen for last. Okay? All right, so we're going to do carbon first. So on this side, I've got 1 carbon, and on this side, I've got 6. So what do I need to multiply my carbon by on my reactant side? 6, right? 6 on both sides. Okay, my carbons are good. Now let's look at my hydrogens. I've got 2 hydrogens here, and I've got 12 right here. So what do I need to multiply my hydrogen on my reactant side so that I have 12? 2 times what equals 12? 6. So I'm going to multiply that by 6. Okay, now I'm going to look at my oxygens. Okay, so 6 times 2 gives me 12, and 6 times 1 gives me 6. So 12 plus 6 gives me 18. Okay? So over here, I've got 6, and I can put a coefficient here. So what do I need more? I need 12 more. So 12 divided by 2, since I've got 2 here, 12 divided by 2 gives me 6. So I need to put a 6 in this box right here. So 6 times 2 will give me 12. So that will give me 18 on this side. Okay? All right, hopefully by now you're getting the hang of it. So, it wouldn't be a bad idea for you to pause this video and see if you can do these next couple on your own, and then take a minute and recheck. Okay? All right, you ready to check? All right, tin. I've got 1 tin, and I've got 1 tin. I'm okay. I've got 1 sodium, and I've got, and I've got 2 sodiums right here. So I need to multiply this by 2. Okay? And then, let's see, I've got 2 times 1. I've got 2 oxygens, so I've got 2 oxygens right here. I've got 2 times 1 for my hydrogen, and I've got 2 hydrogens right here. So all I needed to do was put a coefficient of 2. How'd you do there? All right. Oh, it looks like we've got another one that's just carbon, hydrogen, and oxygen. So remember, I said to do carbon first. Okay, let's look at carbon. 8 and 1. So let's put in an 8 here. Whoa. Let's not do that. We're going to put in an 8 here. Why does it keep on moving on me? Okay. I've got 18 hydrogens. What can I multiply 2 by to give me 18? 2 times 9? Did you say 9? Okay. Now, let's count up all my oxygens on this side. So 8 times 2 gives me 16. 9 times 1 gives me 9 more. 16 plus 9 is 25. Okay, how do I get 25 oxygens out of groups of 2? Can I divide 25 by 2? I can, but does it give me a whole number? No, it doesn't. It gives me 12.5. And remember, my coefficients need to be whole numbers. So what that means that I need to do is I need to double everything. So I'm going to go back through and I'm going to double everything. So 2 times 1, 8 times 2 will give me 16. 9 times 2 will give me 18. Okay, so let's refigure our oxygens. So let's actually go back. So 2 times 8 is 16, so 16 carbons. 2 times 18 is 36 hydrogens, right? 18 times 2 is 36 hydrogens. Okay, here we go. Oxygen. 16 times 2 gives me 32, right? And 18 times 1 gives me 18. So what's 32 plus 18? Did you say 50? What's 50 divided by 2 since we have to do groups of 2? Hopefully you said 25. How'd you do? So notice that I had to go back and change some of these coefficients just to double things up. So until you're really good at this and comfortable with this, I suggest you use a pencil when you're doing these. Okay? All right, let's do this next one. Aluminum. We know what aluminum is. It's Al. Oh, actually, we don't have to write it. We've got 1 aluminum. Come on, let me erase. We've got 1 aluminum. We're okay here. We've got 2, so let's multiply that by 2. Okay, I've got 2 hydrogens, and I've got 2 hydrogens. Ooh, I've got my sulfate group. I've got one sulfate group, and here I've got 3. So I need to multiply my sulfuric acid by 3 to get enough sulfate groups. 3 times 2 now gives me 6 hydrogens, so I need to go back and put a 3 in front of my hydrogens. Okay, how did you do with that one? All right, these next ones are going to be a little bit more tricky because I'm giving you words, which means that you have to come up with the formulas. Okay, so let me show you how coming up with the formulas, it's just like our formula writing. So formula writing is really important. Okay, so iron. Our symbol for iron is Fe, right? And it's a solid. And fluorine gas, remember, fluorine, Brinkelhoff. Yeah, fluorine is one of the diatomics, so it comes in groups of 2. What does that 3 tell me about the iron? Did you say it's charged iron plus 3? Yep. Okay, what's the charge on fluorine when it acquires a charge? Do you guys remember? Fluorine is in our -1 column. Okay, so fluorine is -1. So what ratio am I going to use to put them together? Remember, the sum of the charges have to equal 0. So if I have a +3 and -1, what's the least common multiple? Did you say 3? So how many irons do I need to get to a +3? I need 1 of them, right? I need 1 of these. How many fluorines do I need to get to a -3? I need 3. So I need 1 iron and I need 3 fluorines. Okay? So there's our skeleton. So remember, when we are writing an equation, the first thing is to write the formulas. Pay attention to the charges and the diatomics. Okay? Don't even worry about balancing the equation. Just write the formulas, get the skeleton equation down first. Then, after you're done writing the correct formulas, then you go back and balance the equation. Go back and balance the skeleton equation. Okay? So the very first thing, just worry about writing the formulas and creating that skeleton equation. Okay, so we're going to go back and we're going to now balance this skeleton equation. Okay, so I've got 1 iron, 1 iron. I'm okay. I've got 2 fluorines and I've got 3 fluorines. So what's the least common multiple between 2 and 3? Did you say 6? Yeah. So what do I need to multiply 2 by to get 6 fluorines? 3. And what do I need to multiply 3 by to get 6 iron 3 fluorides? I need to multiply this by 2. So that means I've multiplied by my iron by 2. So I need to multiply this by 2 as well. Okay? Let's do our next one. Sulfur trioxide. So sulfur, tri means 3. So 3 oxygens in the gas state. Water, H2O in the liquid state. And sulfuric acid. Ics come from 8s, right? So what is sulfate? Take a minute, look it up. Did you find this? SO4 -2. So if hydrogen is a +1, how many hydrogens do I need to put on there to match that -2 charge? Did you say 2? H2SO4, and this is in the aqueous state or dissolved in water. Okay, so there's our skeleton. Notice how I wrote the skeleton equation first. Now I'm going to go back and balance that equation. So let's go back and balance the equation here. So I've got 1 sulfur. I've got 1 sulfur. I've got 2 hydrogens. I've got 2 hydrogens. I've got 3 plus 1 oxygen. That gives me 4 oxygens total. And here I've got 4 oxygens total. So this is one of the rare ones where our skeleton equation is actually balanced. It's actually balanced. So it's okay. All right, here's another example. Sodium, solid. So sodium in the solid form, magnesium. What's the charge that magnesium acquires? Do you see that magnesium's in that second column, so it's going to be a positive 2? So magnesium, let's start this over. Magnesium is a positive 2. Let's see, iodine. What charge does iodine have? If I look at my periodic table, iodine's down here. It is a -1. Okay, so what ratio am I going to use to put those together? Did you say 1 magnesium and 2 iodines? And this is in the aqueous state. And then it goes to make sodium. Sodium didn't have a charge in the reactant side, so let's look and see what charge sodium acquires. Sodium is a positive 1. So sodium is a positive 1, and iodine, when we look at it, is a -1. It lost my magnesium iodide, but not my reactant arrow. So when I look at my sodium iodide, it's going to be a 1-to-1 ratio here. 1 sodium to 1 iodine, and that is going to be aqueous. And then magnesium is going to be off by itself in the solid state. Okay, there's my skeleton. Okay, write your formulas first. So write the formulas first, pay attention to charges, pay attention to your diatomics, then go back and balance the equation. Okay? You can't do it all in one step. It's a 2-step process. Okay, let's balance this. So 1 sodium, I'm okay here. 1 magnesium, I'm okay here. 2 iodine, I just have 1 iodine here. So I'm going to multiply this, which means that I need to go back and multiply my sodiums. Okay? We feeling pretty good about that? All right. One more example. Vanadium. Vanadium as a solid. Oxygen. This is one of our diatomics, right? Brinkel-Hoff. So oxygen is a diatomic. Vanadium. So vanadium, that's going to be a +5 right there. That V tells me it's a +5. What charge does oxygen acquire? Let's look. Oxygen acquires a -2 charge. Okay, so oxygen, -2. So what's my least common multiple between 2 and 5? Did you say 10? It is 10. So how many +5s do I need to get to a +10? I need 2 of them, right? And how many -2s do I need to get to a -10? I need 5 of them. And this will be in the solid state. Okay, so there's my skeleton. Now I'm going to go back and I'm going to, you guessed it, I'm going to balance. Okay, 1 vanadium, 2 vanadiums. So I need to multiply this by 2. 2 oxygens, 5 oxygens. Once again, LCM, right? What's my least common multiple between 2 and 5? It's 10. So I need to multiply my oxygen by 5 to get me 10 oxygens, and I need to multiply my vanadium 5 oxide by 2 to get me 10 oxygens, which means I need to go 2 times 2 gives me 4 vanadiums, right? So I need to go back and I need to change this to a 4. How'd you do on that? All right, so your homework today is going to be a lot like this. You're going to balance equations, figure out the coefficients that you need to have. If you have any questions or concerns, please come talk to me or email me. Thanks. Have a good day. Bye.